Oh, by the way, I even started figuring out a way to draw on these slides. But here, see, so I can do it. It's really kind of hard. So, anyway, so I can start drawing. It's not very easy just yet. But oh, now I want to erase all ink on the slide. There we go, and then you can just erase it. Okay, so let's go here and we'll do the laser pointer. And let's do this. Okay. All right, so as you may recall, what we talked about last week, last Thursday, okay, was a uniform distribution. And basically what we had there is we created a rectangle. Okay, we generally started at 0 and went up to 30, and then we figured out what were the probabilities based upon a density formula, which is nothing more than a discussion on what is the area under that curve. It's not really a curve because it's a uniform distribution, but what's the area under a certain part of that uniform distribution, right? And so then what we've done is we have moved toward a normal distribution, okay, which, as you know, looks like the standard bell-shaped curve of days gone by, okay? And so with a uniform distribution, it's really easy to figure out what the area is and what the probability is under that curve between two numbers, or an x1 and an x2, right? But now when you do a bell-shaped curve, it becomes near to impossible, but there's formulas out there, there's tables out there, and the computer, a lot of the computer programs will do that for you as well. So let's talk a little bit more, okay? And just to bring it back into where we were last week, this is the distribution curve, okay? And before the uniform, we just had a triangle, right? And it's really easy to find the area of a triangle, base times the height. Okay. But now you have this triangle. What about all this up here? How do you find the area for something between here and here? Okay. You can't really do it with a standard base times the height. Okay. And that's where this is going as far as understanding the probability goes. Okay. And so here you have, okay, same old, you have the mean, okay, the median and the mode, and this is for a normal distribution, normalcy of distribution. When in doubt in this course, we assume normalcy of distribution, because if you don't have normalcy of distribution, you got to do a whole another set of tests. So that's why here we always assume normalcy of distribution, and therefore we can do what's called parametric tests as opposed to non-parametric tests. So that's the reason that we talk about normalcy of distribution in some sense. Okay. All right, so here we have this family. Sometimes you can think of these as a family of distributions, okay? And these are just different at different means, okay? 25, it can be 10. It could be, we're on a continuous now as opposed to discrete, so it could be a 5.3 minus 5.3, right? Okay. And it can also be 0. And 0 is actually where we're going to go with this as we translate to what's called a scale of z. And we'll talk more about that here in just a few minutes. All right. Now we also have the standard deviation. So not only can the means be different, the standard deviations can be different. And here you have what's peak. Oh, it's a higher peak, or this is called kurtosis, and that's where we left it off, because we said on Thursday, we said in the event that you're at a social event, in a pub, or whatever the case might be, out having dinner, and the term kurtosis comes up, you can join in, because you know that all that means is how much peakiness you have in a distribution curve. Okay. All right. And the tighter the standard deviation, okay, the tighter the standard deviation relative to the mean, the more peakiness or kurtosis you pick up. Okay, key concept here. 0.5 and 0.5. If you took all the numbers under this curve, okay, and added up all the probabilities, what would be the probability that you get every number under that curve? 1, that's right, 1.0. And how did you get that, Casey?
Because it's all covered underneath the curve, so the full range of data is covered.
Yeah, 0.5 and a 0.5 is 1, so it's a 100%. And keep in mind that probability is probability. As you may recall, we went from 0%, okay, in any probability, okay, you always have a 0%, which is absolutely positively not going to happen. And then you have 1.0 where it absolutely positively is going to happen, and everything in between is somewhere between a coin toss and either not going to happen or is definitely going to happen. Right? The Cincinnati Reds, I think this is official. In fact, I think we can now say that since the Cardinals beat the Dodgers, what is the probability that the Dodgers are going to win the World Series? Shane. Who's the baseball guy? Is it Shane? Yeah. All right, you were the pitcher, right?
Yeah, I don't think that series is over.
Really? Is there a protest?
2-1.
Oh, you're right. Oh, that's not good. That's right. The headline was yeah, you're right. So there is still a metaphysical possibility. Oh, here we go. The Los Angeles Angels and Albert Pujols. Love that guy. All right. What's the probability the Los Angeles Angels are going to win the World Series? That would be 0. All right. And so these are all the numbers. So if you put 1,000, 10,000, a billion numbers into a hat, right, and pulled it out, what's the probability that you're going to be somewhere between here and here as far as the value of x goes? And you pull out one number. What's the probability that you're going to be between this value here and this value here? 100%. That's right. Now, what's the probability that you're going to be between the mean and the most extreme point to the positive? Yeah. Okay. And so what we'll do here is we'll start manipulating this curve to understand probabilities for outcomes. And outcomes are defined as, it can be an individual outcome, a number, or it can be a combination of events. Okay? And the combination of events that you would have is what's the probability that if this runs from 0 to 100 and this were 50, okay, what's the probability that you're going to get between 37 and 72? And we'll be able to calculate that. Okay. And the way we're going to do that is we're going to rely on the empirical rule. We've covered this before, but it's going to become even more important. Okay, is that plus or minus 1 standard deviation? Okay, you've already done that a number of times. It should be starting to sound a little bit familiar. Plus or minus 1 standard deviation. Okay, 68% chance. 2 standard deviations, 95%, más o menos, and virtually all at plus or minus 3 standard deviations. So, if your mean is 30, okay, and your standard deviation is 10, okay, if you go out 1 standard deviation, what's the value at 1 standard deviation plus 1 standard deviation? 40. What's the value at minus 1 standard deviation, someone other than Casey? 20, that's right. Okay, so now you have these 100 numbers, you put your hand in the hat, you pull it out, and you have a 68% 1 standard deviation. We'll get a number between 20 and 40. You got 2 standard deviations. What's the value at 2 standard deviations, positive 2 standard deviations, Jesse? No, yeah, well that would be true. At 2 standard deviations plus or minus 2 standard deviations, but what would the actual value be for plus 2 standard deviations? The mean is, what did we say, 30, and the standard deviation is 10? Mm-hmm. Mm-hmm. It would actually be 40. No, it would be 50. Yes, you're right, because the mean was 30. Yes, it would be 50. That's exactly right. Good. Okay. There you go. So 50. Now, what about negative 2 standard deviations? Jake. What would the value be at negative 2 standard deviations if your mean is 30 and your standard deviation, one standard deviation is 10? That's right. Okay. So now, same old, same old. You put all these numbers in the hat, you pull the number out of a hat, and what's the probability that that number that you choose is going to be somewhere between 10 and 50? 95%. All right. All right. But now, okay, so that gets easier. And as we talked before, when you got 3 standard deviations, you got virtually everything. So there's almost a 100% chance that you're going to get a number that's between 0 and 60. But now, what about if you have 22 or 21? It's not quite as easy, because you say, okay, well, plus or minus 1 standard deviation is 40 and 20. What if it comes in at 32? Now what do you do? You look for the area. You're going to start looking for the area under the curve, and what they call, it's called z-values. Okay. One is the empirical rule. Here it is one more time, and the only difference between this and a sample, if this were a sample, okay, this would be x bar, this would be x bar plus 1 and then a small s. Okay, so here, as soon as you see mu and sigma, okay, you know that you're talking about an entire population. The next chapter is where we'll start talking about sampling. All right. All right. And so between 0 and 1, you have a standard normal probability distribution. And the way we denote a standard probability distribution on a scale of z is we take everything to 0. We peg everything back to the scale of z. Critical concept. Okay? You have 0. That is the mean of any measurement that's out there. The scale of z can be used for miles, meters, gallons, liters. What's another unit of measure? What is it? What is it? Yeah, planes. What did you say? Oh, pints. Pints. I just said planes. That's my Midwest accent ear. Yeah, pints. Pints. I mean, pick another one. Pick any unit of measure. Just go crazy. Light years. I can take it back to a scale of z. Pick another unit of measure. Any unit of measure. What's another unit of measure?
Moles.
What is it?
Moles.
Bowls.
Moles.
Moles. As in moles and scientific moles. Okay, good. Yeah. I thought you were playing whack-a-mole or something.
Yeah.
Moles. Yes. Okay, going back to the scientific days. Is that in biology? Chemistry. Moles. Yeah. I didn't do too well in chemistry. Anyway, so yeah, anything you can take. I mean, if you want to take it, let's take just something totally science fiction. Called it eons. Actually, that's not totally science fiction. We can take anything and we can move it toward any scale we want, and we can take it back to a scale of z. This is much like the U.S. dollar. Okay, every currency in the world, okay, most every currency in the world is pegged back to the dollar. Okay, even the Russians are trying to find a way to not peg their currency back to the dollar. So the scale of z is just the common currency, if you will, of statistics. so here's how we convert any scale, any number, any negative number, positive number, continuous, discrete, whatever the number is, to a scale of z. It's x minus mu over sigma. So what was the example you had? It was moles. Okay, it can be moles. So you have x moles minus the mu for all the moles divided by the standard deviation. And this is for the population only. And that gets you to a scale of z. Okay. If we had, what was yours? It was, who had pints? Pints. If it's pints, 10 pints minus 20 pints divided by the standard deviation, which you'd have to be given, or you'd have to be able to calculate, of 3. Okay. So you convert everything back to a scale of z. Okay. The common currency of statistics, as you know it right now. So let's take an example. Okay. This is an auto parts store, but it's a Pep Zone. What do they call them here? What's an auto parts store? AutoZone. Yeah. Pep Boys. Yeah, they combine Pep Boys and AutoZone. All right. So when the stock of oil drops to 20 gallons, a replenishment order is placed. Okay. Managers that they're due to stock while waiting for replenishment. Because if you walk into the AutoZone and you want this oil drop, okay, this multi-grade motor oil, okay, and you walk in the store and it's your favorite motor oil, you walk in, it's not there. What are you going to do? Yeah, you're going to go down the street and get another one, okay, or to another store, right? So you don't want to be out of stock. And here's how you would calculate this. You'd have to be given the mean, which is 15 gallons, okay, and a standard deviation of 6. And so you want to calculate what is the probability that it's going to be greater than 20. All right. Now, this is an engineering trick. Or this is the first, the first day you walk into engineering. Are you an engineering major or a chem major? Why were you taking chem? Just because you have to? Yeah. At any rate, first day of chemistry, Chem 5, in any basic engineering course. Okay. What's the first thing that they tell you to do when you're given a word problem like this? What do you look for? The answer. True. And that's the solve for. In the old days, it used to be called find. And they still teach this in engineering school across the world today. First thing you start with is, what are your givens? All right. And then, what are you solving for? In this one, okay, what are the givens? And look for the numbers. What are the givens here? What is it? Mu equals 15. What else have we given? Standard deviation. What's the standard deviation? What is it? 6 gallons. Okay. Doesn't matter. It can be gallons. It can be pints. It can be, the moles. Doesn't matter. And what's the last one we're given? Anything else we're given? Yeah. And that's kind of comes down into here, where you're looking for the probability that x is greater than or equal, or greater than, let's just greater than 20. And that's what you're solving for. This is how you take any word problem and convert it into something that might make more sense to you. This is how I would do it. This was drilled in us in engineering school from the day we got there until the day they gave us the diploma. Okay? And so now you say, okay, well, what am I really trying to do? I'm just trying to find greater than 20. Okay? So I come in here, I draw out my bell curve. And I know that my mu is 15. I know my standard deviation is equal to 6. And I'm trying to find the area under the curve at greater than 20. Now the good news is we know that the whole thing is 1.0. We already determined that, right? 5 minutes ago. Now we say this is 0.5, this is 0.5, but how do we determine 20? And that's where we go to our handy dandy formula. Z, we convert everything to a scale of Z, the common currency of statistics. And we say, okay, what is the value of Z? We know at the mean, the value of Z is 0 every time. Then all we have to do is find the value of Z at 20. Make sense? Okay. How would we go about doing that? If you set up the problem from this point forward, every problem that we're doing from this point forward, using this given, solve for, draw the visual, you will have a much better chance of not getting lost. I assure you. You can do it, you know, everybody's going to do this a different way. This is just how I was trained, 5 years, however long it took me to get through engineering school, right? And so now we need to convert to this 20 to a scale of Z. We already know what the mean is. The mean's always 0 on a scale of Z. And here is the number. Calculate out 0.83. So now we know that the value of Z at 20 is 0.83. But if you used plus or minus 1 standard deviation, what's plus or minus 1 standard deviation here? 15 plus 6 would be 21. Be easy to calculate. But we got now we're at 20 and 0.83. So how do you do that? What we do here is you're going to go to the back of your textbook. Okay, and there's a handy dandy Z chart. Much like there was a Poisson. And this starts on page, hopefully I don't have it this torn out. The Z charts start on, here we go, on page 974. It's the very first table up. Well, you can share with one of those guys if you want. Or, gotta look here. Okay. So, the value of Z at 0.83. Okay, here's the value of Z, 0.83 is 0.7967. If you look on the table, don't look at that one. Look on the table on page 975, and if the value of Z, okay, is equal to what did we say, 0.83, that probability is 0.7967. But keep in mind, that's everything back here is 0.7967. And you're looking for what's greater than 20. So everything less than 20 is about 80%. The probability of more than 20 is about 20 is 20%, or slightly more than 20%. So I did that. Look for your z value, calculate your z. Then, once you have all your givens, you calculate your z, you go to your table, 0.83, you look up at your handy dandy table, it's the z chart in the back, and you'll have to be given the z chart. And a 0.83, you go 0.8 on z down the left column, and then 3, so it's 0.7967, about 80%. So what that's telling you is there is approximately an 80% chance that you'll get a number less than 20, but conversely, there's a 20% chance you're going to get a number greater than 20. And that's how you convert everything to the common scale of z, which in statistics is the common currency. So here's an exercise for you. And work in your teams on this one. So we have determined at this point that between +1 and -1 on a scale of z, it's 68%. So that would be the value for between 900 and 1100. We talked about the table already. And it doesn't always end up being 1, doesn't always end up being an even number, okay? And so, or a whole number like a 1 or a 0 or a 2. And so you can get any value of z in between 0 and 1, 0 and 2, 0 and 3, 0 and -1, 0 and -2, 0 and -3, and it's generally around 1 minus is near to the same thing as a standard deviation, if not exact, except you're all on the scale of z. Right. So if you had a 0.83, we already did that, 0.7987. And we've already solved this. 1 minus 0.7987, this was the problem we had before, using what you did in the example. Only you don't have, it didn't come out nice and neat for you with 1 and -1. Here it was 0.83. And the value for z at 0.83, 1 minus that gives you the area under that curve. And in fact, in the example we had before, that'd be everything greater than 20. Greater than 20. Now, let's pull out of this a little bit. So what? Now that we have this probability of 20, so what? What does that mean? What does 0.2 mean? Yeah. That if you did an ordering it at 20, that you were going to run out of stock 20% of the time. But the good news is you're going to be there 80% of the time. Is that good or bad? Could be good, could be bad. What you could do is you could actually, from there, you could calculate, and from an accounting standpoint, you could say, okay, if 20% of the time I'm not going to have enough stock, how much sales am I losing? And how much revenue am I losing? How much growth, how much margin am I losing? And then you say, what's wrong with carrying a few more gallons? If I can take that up to, I'm in stock 95% of the time. I carry 30 gallons or whatever the number is. Probably 40, I guess it would be. So I stock 40. What am I losing by stocking 40? What's wrong with stocking 40 when you may not need it? Just sits on the shelf, takes up shelf space. You work at a Best Buy. Do you have unlimited shelf space at the Best Buy? It's very crowded, actually, these days at the Best Buy. Guarantee you. Shelf space is a premium. Okay. What you do, you take and put in the warehouse. Do you have unlimited warehouse space? No. So now you have the business decision is, okay, how much money am I losing? How much sales am I losing based upon a 20% probability? And you can actually calculate that. That's the business part of what you as business people will be determining. Are you going to be calculating 20%? Maybe yes, maybe no. But somehow, somewhere, somebody has determined here is the order quantity that we want to, or the minimum stock we want to have at all times. Someone back at the headquarters of Best Buy. Here's what we drew before, 20%. This was the value of Z, 0.83, and we looked it up on the table. 0.7987, but it's everything not under this curve, this part of the curve that's important for this problem. And so what you're going to do is you're just going to keep manipulating and looking at the visualization of situations from this point forward. Everything is going to be based upon, from near to this point forward, up through halfway through BANA 2 is going to be using some form of this type of discussion where you're looking for the area under a curve. And you see where it was derived from. It was derived from the empirical rule. The empirical rule says plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations, 68, 95, virtually all. And so all you're doing is, in some respects, this is a Schulteism. You're kind of extrapolating, in some respects, what lies in between. And the good news here is that if you created a chart for every situation, every unit of measure out there, how big of a room would you need? For pints, for eons, for moles. Thank you for that one. That really brought back good memories. Actually, not so good memories. Thank you for that, though. Moles. What was another one of what was another one of the units of measure? You'd have a table that would go on for infinitum. So infinitum, it'd probably take up. I mean, if you had a table for every unit of measure in the world that's known to man or woman, mankind, let's call it, you may not have enough space in the entire world, enough warehouse space. So that's why we take everything to the common currency of statistics, the scale of Z. It's a great technique to understand probability. We already did this one, 790 to 1,000. Did we do 790? No, we didn't. Let's do this one now. No. Yeah, do this one. Please. So it's not going to end up being as neat and tidy as you are used to. 3 minutes. I know. You got 5 minutes. You got 5-6 minutes early on Thursdays, and there's no class this week. All right. I know. Here's a good one. Now you're going to start hearing this more. You're going to start hearing this discussion more and more. What is the probability that they won't run out of stock more than 5% of the time? That's called P.05. And this is what most companies or most people start out making decisions at. P.05. All right. That means there's a 5% chance they're still going to run out of stock, like we talked before. But there's a 95% chance that they're not going to run out of stock. All right. Would you take those odds? Probably not a bad, especially if you had a little extra room in the warehouse. But if you were scrunched on space, you might bump that down to 90%. And all you do is you'll look for the value at at a z of 2 standard deviations out and everything underneath. All right. And this is it. So what you're doing here is you've got p.05. You found the z value, and this is how it's denoted mathematically, z.05. And if you went and looked at the z value of 0.05, you'd come up with 0.05 if you want to confirm that in the z chart. And so the way you get this, what is the reorder point, okay, at 95%, okay, it would be right here. But there is a 5% chance you're going to run out. You went to the tables, convert it, and here we go. And now you can kind of back into this a little bit. So you can manipulate these numbers mathematically as well. If you're trying to find what is the exact point in this situation, x, and the formula we had before was z was equal to x minus mu over sigma. You just reconfigured that formula where you can actually figure out the value of x at where you need to reorder, how many gallons you need to order, which in this case would be 25. And you would run out of, in theory, and hopefully in practice, you would run out of stock 5% of the time. But 95% of the time a customer walks in the door, you got it. And you just round it up, assuming that it was 24.87, but you'd round it up a little bit to 25. And you can do this one at home, but basically what you're doing is you're manipulating that formula, z is equal to x minus mu over sigma, multiple times and from different perspectives to find an answer, which in this case was what should the guarantee or warranty be for these tires. And this is actually how they do it. They say, okay, we know that historically our tires will wear out at this miles, or these many miles. Here's the standard deviation. What should our guarantee be? It's a practical application. Hey, on the quiz that's due next Tuesday, there is a problem in there on exponential probability. So make sure you cover those 3 pages at the end and make sure you understand that problem before you go in and hopefully emulate as close as possible a exam situation. Yes, sir.
I need the groups joining.
Oh yeah.
I need to get out of the one I'm in and get into another one.
Which I think. Can you just sign up for the other one? I think. Who are you in with?
I can't once I start it up.
Oh, it doesn't let you. Oh, okay, okay, excellent.
What is his name?
Shane, you probably can't.
It's Shane. Yeah. Yeah, probably. Yeah.